Good afternoon, everybody. I'm very happy to be here talking to you about my passion for fossil microbes and searching for life on Mars. So, as you can imagine, the context of the talk is the actual search for life on Mars with the rover Curiosity that's landed in Gale Crater. So yes, the context is Curiosity that's landed in on a delta plane in the Gale Crater and is about to head off towards Mount Sharp to analyze rocks and minerals, especially at the base of the mountain, that are supposed to have been altered, volcanic rocks and minerals that are supposed to have been altered by water. So here's an image of an artistic view of Curiosity on the surface of Mars. And we have, of course, our own mission, rover, ExoMars 2018, which we hope will get off the ground. The objectives of both of these missions is to study the conditions of habitability on the surface of Mars, at least at the landing site, and to search for any eventual traces of life that might be in the rocks and the minerals. So, from my point of view, habitability on a planetary scale it can be defined as the ingredients of life: liquid water, carbon, bioessential elements such as hydrogen, nitrogen, oxygen, phosphorus, and sulfur, as well as the essential nutrients such as transition metals and different kinds of energy, the chemical or light energy. But if we look at things on a microbial scale, scales are vastly different. We have a scale specific to the origin of life, a scale for organisms that are actually in the process of metabolizing living, and a scale for organisms that are simply in a state of survival. So, in terms of an origin of life, the critical limit is the presence of liquid water for the time span that we think is necessary for life to originate. And that's of the order of hundreds of thousands of years, maybe a couple of millions of years. And this is based on an estimate by Leslie Orville, published in 1998. In order to have liquid water on the surface of Mars for this period of time, we would be looking at a crater of the order of 100 kilometers minimum. So that's a difference to the global scale habitability of a planet. In terms of living organisms that are reproducing, metabolizing, these organisms can be opportunistic. They can opportunistically colonize a habitat that's habitable for just a short period of time, a day. They can live for weeks in certain circumstances. And the scale orders completely different, orders of magnitude smaller, from 10 to maybe 1,000 microns. So much smaller spatial and temporal scale. When it comes to surviving, we don't really know how long organisms can survive. Hibernating organisms have been identified in permafrost that's 5 million years old on Antarctica. Although in the last 5 million years, this permafrost will have sort of melted. The organisms could have metabolized for a while, and then as the permafrost became frozen again, then they would go into survival mode. So let's say of survival on the spatial scale up to perhaps 1 million years or so, and the same kind of sorry, that's on the temporal scale, the same kind of spatial scales as living organisms of the order of 10 to 1,000 microns. So as I mentioned before, this means that the habitable zone of the planet doesn't need to cover the whole planet. It can just be a part of it. So this, looking at early Mars, or Mars from this point of view in its early history, Mars, as is illustrated in this artist's view of early Mars, definitely had basins of water that were long-lived and large enough to have perhaps seen an origin of life or life emerging, and the early Earth, in comparison, was basically totally habitable because the early Earth was an ocean planet. So we can say that Mars definitely was conducive to the emergence of life and to the supporting extant life at the surface for a certain period of time. If we look at the global conditions, environmental conditions on both planets in the early part of their history, they're basically very similar. Ocean temperatures on the early Earth were pretty hot because the Earth was, the mantle was much hotter. The Earth was still cooling down, still is cooling down. On Mars, we don't really know what the temperatures of the impact crater basins or the sea on the northern hemisphere of the planet was. Possibly also at least around hydrothermal environments, quite warm, and possibly at the surface cold and maybe even frozen over. The important thing is that the global environment was anoxygenic with CO2 atmosphere, some greenhouse gases, and very, very little oxygen. This meant, at least on the early Earth, relatively acidic global ocean water with some alkaline areas around certain hydrothermal vents, possibly similar on Mars, high rates of radiation to the surfaces of the planet, although, and these values were estimated by Charlie Cockell and his colleague Raven in 2004. So, but organisms were still able to survive under these conditions, as I will show from the early Earth. Very extreme hydrothermalism, extreme volcanism on the early Earth and on early Mars, frequent impacts. And what's important from the microbial point of view is the kinds of habitats. We're basically looking at volcanic and hydrothermal habitats on both planets. And this will influence the type of life that could live on the planets. However, from about 3.8 to about 3.5 billion years ago on Mars, the surface and environmental conditions became inhospitable. Life would have become extinct at the surface of Mars if it was there. But there's a possibility that if life did appear on Mars, that it could have penetrated cracks in the crust and penetrated through to the subsurface aquifers and become cryo-frozen. Sorry about this. I'll just, and this has implications for lifestyles and evolution of life on Mars. As I mentioned, where the environmental conditions were basically anoxygenic, so we're looking at anaerobic organisms that have as their basic nutrient source rocks, volcanic rocks, hydrothermal environments. So probably looking at organisms that were chemotrophs that obtained their energy and carbon from inorganic sources, or in the case of organotrophs that obtained their energy and carbon either from inorganic sources or also from the organics. And I have here some images of the types of organisms that could have occurred on Mars, or could maybe still are on Mars if there's still active life in the subsurface. We have the methanogen Pyrococcus yanashi on the middle left, and the chemolithotroph Citrix, a filamentous sulfur oxidizing microorganism. I've also added hapithermophilic viruses that are associated with organisms such as Pyrococcus yanashi. And I will come back to this right at the end of my talk. But just think that on Earth, viruses appeared very, very early in the history of microbial life. They were probably on the early Earth, although I haven't found any fossil ones yet. And they may well have been important on early Mars. So Before giving you an overview of what we're finding on the early Earth, I'd like to talk a little bit about how the traces of life can be preserved in rocks over geological time, because now I will be talking about geological timescales of 3.5 billion years, which is rather a long time, but this is also the timescale that is relevant for Mars. So basically, we can put this in another way: how do microorganisms fossilize? And they can quite easily. I've done numerous experiments to fossilize microorganisms. So what can be fossilized? Well, the major microbial components are represented by the physical structure, the actual the cells, the colonies they form, or the biofilms, mats, or the microbial extracellular polymeric substances. Then there are also the organic cell components. This means the carbon molecules, their structure, their composition, elemental and molecular composition, and various types of evidence of cell metabolic activity, such as associated biominerals, or the fractionation of certain elements, such as carbon. Also microbial influence on minerals, such as the corrosion of minerals to obtain nutrients. So all of these features of microbial life can be preserved in the rock record, and I will be showing you examples of all of these. And as I do so, talking about the early life, think about how one could do this on Mars, because we'll be coming back to that at the end. So, getting in the I've made a series of sketches to illustrate how organisms or biosignatures are preserved. So, in this very, very simple sketch, imagine that the oval grey shapes are sedimentary particles, that there are colonies of chemotrophic organisms that have colonized the surfaces of these particles. And the reason I'm using this example is because I will be showing you examples of these. This is on the left is the situation, let's say, in the sediment. We have a waterlogged sediment of volcanic particles with chemotrophic colonies on the surfaces of these volcanic particles. In geological time, with burial of the sediments, the organisms can simply completely degrade, and their organic matter becomes a kind of diffuse cloud of organics disseminated in between the particles. And this happens very frequently in fine-grained anaerobic sediments such as clays. And in the sketch, the organics are shown by this sort of red stippled texture. Another way, these kinds of this kind of preservation can produce what we call biomarkers. The specific molecules of specific components of the organisms can be degraded, and their degraded components can still be recognized up to a certain stage in the organic record, such as straight chain aliphatics, phytane or carotene, polycyclic aliphatics such as hopane, or the polycyclic aromatics such as fluorine, benzopyrene. These molecules, biomarker molecules, however, do not have that cannot be preserved for very, very long geological timescales, and I'm talking about over 2.5 billion years. There has been some controversy over finding biomarkers in 2.7 billion year old sediments in Australia. It's believed that the biomarkers that have been found are actually more recent contaminants, but there are no biomarkers left in sediments that are older than 3 billion years. All the functional groups disappear, and basically what you end up with are just aromatic type of particles. And I will show you some examples of these. Another way that we can have preserved organisms is if in fine-grained sediments, the organisms can simply be squashed within the lithified sediment, especially, for instance, if it's a shale or a clay, but the organisms need to be relatively robust. They need to have a robust outer envelope to survive the squashing. And such structures, for instance, are fossilized spores, such as this one illustrated here on the right. It's what we call an acritarch. It's 1.6 billion years old, and it comes from Australia. So organisms with quite robust cell envelopes can be preserved in plastic sediments in anaerobic conditions. Now, microorganisms can also be fossilized in the same way as larger organisms by having minerals coating them. And these organisms are also preserved in liquefied sediments, either in anaerobic or aerobic environments. In aerobic environments, the organic matter will be completely degraded. In anaerobic environments, you can still have the preservation of organic matter with the fossilized organism. And this is another sketch to illustrate how this happens. Imagine you have organic matter, which is illustrated by this black line here. Functional groups that are part of this organic matter. It could be a cell wall, it could be EPS or any other organic substance. If there are functional groups associated with it, and if it is in the presence of a solution that's saturated in a certain mineral, for instance, silica, calcium, carbonate, or whatever, calcium, the mineral ions fix to the functional groups, and then there's further polymerization. As an example, these are photographs taken from my own experiments to fossilize bacteria. On the left, you have a thin section of amicrobial organisms. The scale bar is 0.1 micron here. The dots that you see around the outer envelope of this organism are minerals that are beginning to precipitate on it. And with time and polymerization, these minerals become a crust. And the dark speckles material that you see inside is the degraded organic matter. So this is how organisms such as microbes or bacteria can be preserved, although they're soft-bodied organisms and they have no outer or hard skeleton. And for instance, here I am illustrating, enlarging the image. We have here an example of this kind, the exquisite preservation that can happen in these cases. Within this quartz crystal, we are seeing here in an etched quartz crystal, half it's partly exposed microorganism. You can see even the cell division and slight wrinkling of the surface of the organism, as well as the associated EPS. Now, this example comes from a rock that's 3.42 billion years old in South Africa, and the organism is still half embedded within the quartz crystal. So just to illustrate how well the fossilization process can work. Now, we have to be very, very careful because of what we call false positives. Microorganisms tend to have very simple shapes and forms, spheres, rods, filaments, and so on, that can be imitated by minerals or non-biological phenomena. And I have here various details of fossil microorganisms that I will be showing a bit later on as well, where you can see the spherical structures and evidence of cell division. But on the bottom right, I'm showing a scanning electron micrograph of abiogenic silica spheres that if you didn't have much experience, you could just automatically think that these were fossil microorganisms. The greatest difference between the abiogenic mineral precipitations and the actual fossilized microorganisms, well, there are two main differences here. These silica spheres are pure silica. There is no organic matter associated with them. Also, they are pure round spherical shapes. If you look at the fossilized colloidal microorganisms, they are pretty irregular, and also there is carbon associated with them, which I'll show later. So we have to be very careful about false positives. And my computer is not, no, here we are. Uh, so in terms of false positives, this is what we call establishment of biogenicity. We have to, we look at a rock, we look at its geological context. This is to study the habitability aspect. Was this rock formed in an environment where life could have lived? It's not the center of lava. Are the structures that we are seeing biogenic, or could they be abiogenic structures? If they are biogenic, at least with respect to life on Earth, this is important. Did they form at the same time as the rock, or are they the product of life forms getting into cracks in the rock more recently and being either fossilized or remaining? So now I'm going to give you some examples of volcanic sediments containing biosignatures from the early Earth. Now, we don't have much material remaining from the early Earth because plate tectonics has, and tectonic processes in general has effectively recycled the crust. So the oldest well-preserved sediments that we have on Earth come from Barberton in South Africa. By the way, South Africa is where I was born, and the Pilbara in northwestern Australia. Both of these, what we call early Archean terrains, are 3.5 billion years, or between 3.3 and 3.5 billion years old. And these are the oldest well-preserved sediments that we can use for searching for traces of life on Earth. So the sedimentary environment of the early Earth was pretty similar to coastal environments on Earth today. However, we have to think in terms of a planet that had no real continents, just volcanoes like Hawaii, Iceland, Ile de la Réunion, etc., sticking out of the ocean. And the kinds of sediments that are preserved are those that have been deposited in relatively shallow waters in sort of lagoons or basins at the edges of these volcanic edifices and on the beaches. So, and I will show you examples of these sediments on the beaches and deposited just in shallow waters and the life forms that are in them. I'll start first using an example from the northwest of Australia, in the Pilbara area. And the example that I will be showing are examples of chemotrophic life, and specifically chemolithotrophic life of the kind that we would hope to find on Mars. Now, I have a series of slides to explain, sorry, this is going automatically, what we geologists do in this field. The sample I'm going to show you is taken from the hill slope here. And for the non-geologist of you, you just see a hill slope with rocks and a bit of green and some sparse trees around. Well, me as a geologist, I see layers of sediments and something softer in between. And I'll explain how this hill formed and what it implies with respect to the early environment of the Earth. Imagine we're on the early Earth, we're on a place like Iceland, we're on the beach, we have layers of sediments. How do we get from an environment like this where we have layers of sediments to a modern day hilltop which has sort of ribs of rock and grass in between it? Well, think of the layers of sediment as having been deposited at different periods of time. We have the oldest sediment at the bottom, the youngest at the top. We're just seeing layers and layers and layers deposited over periods of, let's say, months, maybe a year or so. So this, another one of my sketches, this top image simulates, it's supposed to represent the layers of sedimented volcanic material, the sedimented sands, the black sands. These black sands then become lithified, and they are overlain by layers of lava. So you have alternately layers of lava and layers of sediment, layers of lava and layers of sediment. These layers are then tilted tectonically, and this is what we end up with. The hardest layers of rock are the silicified sediments, Silicified because the early oceans were very much rich in silica, saturated in silica. And in between the layers of sediments, we have the volcanic rocks, which are softer and more eroded. So here we have the layers of sediment. Now, I will show you an image of one of these sedimentary exposures. This is one of the rocks that I've been working on, and the actual examples of early life that I'll be showing you are taken from this portion at the upper left here, which represents a portion in the middle here. I'll show you detail. So this rock, you see a rock that is laminated, dark grey, light grey. These different layers are literally different layers of sediments. The lighter layers are coarser, the darker layers are more fine-grained. And we can also see in this rock fossilized ripples. So we know that this rock was deposited close to the beach. So we already have some information about the environment. Now we'll be looking in more detail in this central area where you can see some sort of spots on one of the grey layers. In terms of, well, on a centimetre scale, this 10 centimetre or 9 centimetre high piece of rock has quite a lot of environments that could have hosted microbial life. At the lower portion, these very fine layers represent sediments that are deposited underwater. So we're looking at grains of volcanic sand, spaces between the volcanic sand pore spaces, and these are habitats that could have hosted microbial life. The grey layer in the middle is an intrusion. It's a hydrothermal vein intrusion. There's a kind of creamy layer right in the middle of the rock. This creamy layer represents an event whereby the seawater retreated and the sediment was exposed to the air. So we actually have a beach surface here, followed by flat-lying layers, which indicate that the water came back and sediments were just simply deposited without wave action. Underneath we have ripples, fossilized ripples indicating wave action. And then right on the beach surface, there are also particles of pumice that are simply embedded in the surface of the beach. And also both the beach surface and the particles of pumice, which is very holy, very scoriaceous, are potential habitats for microbial life. And in fact, I find traces, fossilized traces of microbial life throughout the rock. Each layer has slightly different types of microbial life. And the exposed beach surface that was then resubmerged contains a very fine biofilm with mostly degraded microbial remains. So getting back to the signatures of microbial life forms, the physical structures, the organic cell components, the metabolic activity, I'm going to show you examples of each of these related to this specific rock just now. So we'll look first of all at the physical features, and in this case we'll be looking at the fossilized traces of cells and colonies. For geologists, in order to study the microbial context, for us it's really important to go from the macro scale, looking at the outcrop on the hillside, looking at the hand specimen as I have just shown you, then looking at the microscopic scale. What you're seeing here is a thin section of the rock. It's 30 microns thick, and we're looking at it in transmitted light, optical light. And it's basically like this volcanic sand cemented by silica. So these particles here are the sand particles that we saw on the Iceland beach, and the grey in between is the silica that's cementing them. You'll notice that many of the particles have a kind of dark coating. In actual fact, this dark coating consists largely of carbon. We've used the mapping micro-Raman spectrometer here to map the carbon, which is in green, around the edge of this altered volcanic particle. So we know there's carbon there, but we want to know in what form this carbon is presented. So we have to go to higher resolution using a high resolution scanning electron microscope. And in this image, you see a sort of granular gray image. But looking more closely in the center portion of the image, you see that the granularity is extremely fine, whereas around the edge of the central portion, it's more blocky. The blocky area is the quartz matrix, the quartz cement, and the central part is actually a volcanic particle that's been altered to phyllosilicate. We're going to zoom in and have a look at a portion here at the edge of the particle. At this edge of the particle, as I said, has been altered to phyllosilicate that you can see in the upper part of the image, finely laminated minerals, and these are actually muscovite. And at the bottom right here, you can see the quartz cement. In between, there is a kind of carpet of beads. This carpet of beads is actually the fossilized colony of chemotrophic organisms. We'll have a look in detail at these. Here we're seeing the edge of the microbial colony with respect to the volcanic particle, the altered volcanic particle. And you notice that the beads, there are two size ranges of beads, a larger one and a smaller one, as you can see here in the middle. Many of them are showing cell division, and they're all coated by some kind of a mucus, as you would imagine on a monolayer microbial colony. If we look at in detail at some of these structures, on the bottom left we have a detail. Note the scale here. The scale is 0.5 microns. This structure is about 0.8 microns in diameter. So we're looking at very small scales. We can see cell division in this organism, in which the organism is starting to separate, and you have a meniscus between the newly dividing cell. On the upper right, you can see again different size ranges: the a 0.8 micron cell and a 0.4 micron cell. Again, all of them showing incipient cell division. And in this particular case of the large organism, one part of the cell has died. It's lysed and is deflated. So we've got the living process, cell division, and death, lysis, all preserved. And I repeat, I should be emphasizing the age of this sample. The sample is about 3.5 billion years old. In the same rock, we also find the remains of filamentous organisms, such as this one here. It's about 10 microns long, about a quarter of a micron in thickness, slightly striated surface, and also deflated, therefore dead before it was fossilized. On the right, you can see a chain of quite deflated and obviously dead microorganisms. So we have coccoidal structures, chains of coccoidal structures, filamentous organisms. So a small variety of microbial forms. Now, the big question is, how do we get from a rock like that to a beautifully exposed fossil like that? Well, it ain't easy. And I can tell you I've spent a lot of time trying to work out the best way to do this. So another one of my sketches. Imagine in this grey box. This grey box is our rock, and the red ovals are our microorganisms. The microorganisms have been silicified. The grey area is pure silica. But although the microorganisms have been silicified, they still contain organic matter. So it's basically dirty silica. And here, if we take a rock surface like the one I showed you, where we have the microorganisms, the dirty silica within the pure silica matrix, what we need to do is to etch the surface with acid to eliminate the pure mineral, the quartz matrix, and expose the impure mineral, which is the fossilized microorganism, thus, so that the microorganisms are exposed. I can tell you it's basically trial and error on this one, and But the results are fantastic, as I've shown you this image before, where you see the quartz crystal, the recrystallized quartz with the half-exposed organism coming out with exquisite preservation details. So, what about the evidence of mineral dissolution as representative of cell metabolic activity? These kinds of organisms are sitting on volcanic particles, and they are extracting nutrients out of the particles by dissolving them. So here again, we have a volcanic particle, as I've shown you, coated with carbon, evidence of microbial activity on the surface of it, with the image of the colony coating the particle. Now, in another volcanic particle, we have here in the middle quadrant a thin section that we're looking at in backscatter with a scanning electron microscope. The mid-gray represents the quartz matrix. The light gray represents the volcanic particles. If we zoom in, we can see on this volcanic particle that there are cracks in the surface of it. If we zoom in at the cracks, we see that they end exactly at the edge of the particle. The quartz cements the cracks. And if we zoom in even more with the cracks, with the scanning electron microscope in secondary electrons, we can see that there is organic matter filling them. This organic matter is the remains of the microbial EPS. So this is further evidence of microbial activity actually corroding the volcanic particle to extract the nutrients. What about the carbon molecules themselves? We've seen that the carbon remains. You've seen this now for the third time. The carbon remains. So what can we tell about the carbon? Well, we can trace the carbon in the actual microfossils, as we can see this filament here. If we trace it with the EDX, the carbon, we can determine that it is indeed carbonaceous, that it is indeed a silicified organic structure, looking at the colony of microorganisms that we've seen before. Here also we can trace the carbon associated with the structure. But this just tells us that there is carbon there. It is possible to get more information from the carbon, even though the carbon is extremely degraded. We can get molecular and elemental information about the composition, and we can also get some information about the structure of the carbon molecules. But to illustrate this, I need to show you another example. The other example comes from the Biosignatures chert in Barberton, South Africa. This is a 3.3 billion year old chert. Like the previous one, we're looking at volcanic sediments that are deposited in a beach environment. And again, I want to remind you that there are no recognizable biosignatures, that should be biomarkers as such. Although we can still get some useful information from the carbon. This is a field view of the exposure, beautiful mountain area in South Africa. This is the Biosignatures chert, and with a view in the field of the chert, black and white layered sediments. And this is the actual sample that I'm going to be using to show you. We take a sample of this material, and actually, in order to prepare the sample for searching for traces of life, I just took this particular hand specimen and hammered it, and one of the portions happened to break open on a sediment, on the sediment structure, on the sediment surface. We're looking at layers of sediments here. Broke open on the sediment surface to show a very, very well preserved but very thin microbial mass or microbial biofilm. You can see a kind of film structure here that is coating the surface of the sample. Part of it is overturned and there's a kind of lineation to it. It obviously formed under the effects of flowing currents. And in fact, the film is formed of very fine filaments, about 1/4 of a micron in diameter, and up to tens of microns or more in length. They're very coated in a very thick layer of EPS. Because this structure is actually quite large. Remember the microorganisms I showed you previously were less than a micron in size. The scale bar here is 300 microns. In actual fact, on this particular sediment surface, we have, or I had, 6 square millimeters of microbial film to deal with. I have a lot less now because I've used quite a lot of it. But this enables us to study in more detail the organic matter. Just to place the microbial, give you some information about the microbial matter. I mentioned it was very thin. What we're seeing here, I've taken a cut into the film using the focused ion beam to expose its vertical structure. Now we're seeing at the base the quartz substrate. The points are actually quartz crystals because the substrate has been recrystallized, and it's pushed the recrystallized quartz is pushing into the base of the microbial mat, which is about 10 microns thick. There is a thin layer of silica coating the mat, and it is that which preserved it. But the whole mat itself is also permeated with silica. We'll have a look at the details now. So this was the trench that I showed you previously to study the actual vertical structure of the microbial mat in situ. But we make very thin slices of the mat to study using different techniques. A 19 nanometer thick thin slice for doing very fine detailed work with a transmission electron microscope, and a thicker slice, 3 microns thick, for doing elemental and or for studying the elemental composition and the molecular composition of the microbial mat. Now, with the high resolution transmission electron microscope, we can look at the organic carbon that's still preserved in the mat, and we can see small domains of organic carbon. These domains represent 1 to 3 nanometer sized fringes, and they are the order of in size they're of the size of aromatic molecules. In terms of looking at the elemental composition of the organic matter, we can use the nanosims. Yves Marocchi at the Paris Museum has been helping me with this. This is our section here. It's 10 microns thick, about 15 microns in diameter. And we're looking at the distribution of carbon and nitrogen here. The yellow-orange spots are the hot spots, and in fact, there's carbon just all through most of the mat. The lower part is the highly silicified part, and the upper part of the mat was the active part of the mat, which is less mineralized compared to the lower part of the mat, except for this hot spot here. We can also look at another one of the bioessential elements, sulfur. Map the composition, the presence of sulfur, which corresponds to very strongly to the presence of carbon and nitrogen. It's possible to do a profile across the structure. Again, remember where it's 10 microns thick. So we can profile the carbon and the nitrogen, which is the blue line, and showing the hot spot at the top here. We can look at the sulfur, which is the red line, showing that the sulfur is present more or less all the way through, with a slight increase at the top of the mat layer. But if you look at the silicon, you'll see that silica permeates the whole of the mat right the way through. It's that which preserved the microbial mat. Just in the same way that the sediments were silicified because seawater was rich in and saturated in silica, the organic remains, whether they're microbial colonies on the surfaces of volcanic particles or microbial mats forming on the surfaces of these volcanic sediments, they are preserved by silica permeation. Now, the fact of having these samples allows us also to do detailed in situ analysis to identify the nature of the molecular, the organic molecules. We have this layer of almost pure organic carbon at the surface of the microbial mat, and using synchrotron radiation and microzones at the sulfur K edge with colleagues Laurence Lemel and Alex Simiovici, we have been able to identify one of the heterocyclic organic molecules as biosine. We also see the presence of sulfate within the bulk of the mat. And using on the original sample, Volker Thiem and Christina Heim at the University of Göttingen have used toxins to identify other aromatic fragments, the largest of which is C14, and they found phenanthrene and anthracene. Now, all of these molecules are very, very basic. You could call them PAHs, polycyclic aromatic hydrocarbons. The thing that differentiates these molecules from those that we find in meteorites, for instance, abiogenic carbon molecules, is that they are more complex, slightly more complex. And in terms of looking at another way of looking at metabolic activity is to look at fractionated isotopes, and I'm going to show you an example here using carbon. If we take the bulk rock, the whole rock, and crush it up, this particular rock has a carbon content of 0.01%, which is very low. The bulk carbon isotope signature is -22.7. If we take just the black carbon-rich layers in the rock, the organic carbon content is higher, 0.07%, and the black layers have a carbon signature of -26.8%. These are values that are consistent with microbial fractionation. We have done some preliminary in situ work with Marc Chaucidon, Claire Rollion-Bard at the University of Nancy, and I've done this with Barbara Cavalazzi, who's now in Bologna. There we're getting a range of values from -20 to -38 per mil, with an average of -28 per mil. So now, transposing this to Mars, I've almost finished now. What does this tell us about how we're going to look for features on Mars? Getting back to our biosignatures of chemotrophic life forms, we have the physical structures, evidence of metabolic activity, the cell organic components. What could we find in situ on Mars? Well, if we look at the instruments that are on the Curiosity rover that will be on the ExoMars rover, we have instruments that help us to identify the geological context, look at the outcrops of the rocks, the textures of the rocks, structure of the rocks, the various cameras, microscopes, and so on. There are instruments that will help us identify the mineralogy of the rocks, Raman, infrared spectrometry, XRD. We can also get some information about the elemental composition of the rocks using XRS and APXS. In terms of looking for traces of life, Curiosity has the SAM instrument, which is a mass spectrometer, which has a gas chromatograph, and I've forgotten what the TLS is. On ExoMars, we will have a mass spectrometer that can also analyze molecules that are produced by laser desorption. So it's possible to look at the organic molecules, the composition, the molecular composition, but to what degree? We know that, the instruments on missions are small, they have little power and reduced resolution compared to the instruments on Earth in a terrestrial laboratory. So with this instrument payload, what could we find on Mars? Physical structures. Well, the microfossils will be far too small to see. I haven't spoken about clotted frag bricks, but we won't be able to see those either. We could eventually see large-scale structures, such as microbial mounds, if they are produced. In terms of evidence of metabolic activity, well, there are a variety of biominerals, including calcite, that have been produced, but all of these minerals can be produced by abiogenic processes. In terms of element concentration, well, organic matter actually concentrates certain elements, but then so do minerals. What about the fractionated isotopes? Well, we could analyze the carbon isotopes, but we still need to have a good understanding about the abiogenic carbon signature on Mars, the carbonate signature on Mars. The instrumentation on the 2 missions can give us some information about the carbon molecules. We should be able to get some information about the composition and the structure of the carbon molecules, but to a much lesser degree than that which we can obtain in a terrestrial laboratory. Well, if we brought any of these, a particularly interesting sample from Mars back to a terrestrial laboratory, what could we find? Well, of course, we can study everything. So my bottom line is that we need to bring materials back from Mars, but we can do a lot of work, preliminary work, looking at the context on the surface of Mars. So I'm just going to show a few of the images that you will all have seen from the Curiosity rover of the Delta floodplain and the base of Mount Sharp, the nice laminated structures at the base of Mount Sharp. This volcanic rock, Ventifact, that has been very nicely imaged with the microscope and analyzed with ChemCam to give a very just general volcanic composition, basaltic composition. We have seen also evidence of water in these structures, these conglomerates that have been produced by streams, ephemeral streams. My question is, what if life on Mars is even smaller and more primitive than early terrestrial life? What kind of a challenge does that pose for us? So, here to end my talk, I will give you a little conundrum. I spoke about viruses and fossilized cells. Well, viruses, like microorganisms, can be fossilized. My former PhD student, Frances Westall, effectively fossilized viruses. Look at the size there, 50 nanometers. This is the fossilized version of this cell here. I would not be able to identify a fossil virus on the basis of this. Now, if we put it into the sedimentological context, here we have our 3.5 billion-year-old sediments, volcanic sediments, nicely preserved. I have put into context here the kinds of microorganisms that occur in this particular sediment, the fossilized microorganisms, the fossil chemotrophs. Now let's have a look at the fossil viruses, what they would look like. This is what we would be seeing, and here is a scale bar here at 1 micron. So I think we have a great challenge ahead of us, and I think we need to work to make sure that the samples that are going to come back to Earth are well chosen, well characterized on the surface. And I don't know if I'll be around to study the return samples myself, but I hope that some of the younger people listening to this talk can. Thank you very much. I'm ready for questions now.
So I have a few questions. The first question will be from Adam Watson.
Hello. Maybe I missed something. Oops, sorry. Maybe I missed something, but I would like to come back to the table when you compare the environments of Mars and Earth, and you told there that the irradiation of Mars and Earth are the same. Why?
The flux of UV radiation, do you mean? Well, actually, this is an estimate from Charles Cockell and Raven in their publication 2004, and I should have made a comment that I'm not talking about here about the total radiation radiation flux. It's the DNA-weighted radiation, and that's UVB. So just the UVB radiation, flux of radiation.
Yes, but I mean the number of watts per square meter. Why it is the same? Because Mars and Earth are on different distances from Sun, so I think that this amount of energy should be smaller for Mars than for Earth.
Well, that's a fair comment, and I will contact Charlie Coquel and discuss this with him. I just took these values verbatim, and maybe I should not have done so. But your comment is relevant, so I will see if it's necessary to correct this value.
Thank you very much.
Thank you. I have now a question from Eva Shushkevich.
Thanks a lot. Thanks, Francis, for a wonderful talk.
Thank you, Eva.
And I'm really astonished what you can do with all those rocks. I would like to a little bit extend maybe the topic you covered. So sorry for that, but I'm sort of very curious about one technique which is, I mean, not used by Curiosity now, but it was used by Phoenix. I mean calorimetry. And would you comment on, I mean, what kind of experiments or what kind of properties you can find out sending again calorimeter on Mars, and if you think that it's really good idea for the next Mars missions?
Well, you've asked a very good question that I'm not too sure that I can really answer. I'm not 100% sure exactly what the calorimeter can measure, and you asking me what it can do. I can't answer that because I don't really know. I don't know if perhaps there is somebody else who's listening who has more information about the calorimeter.
Okay, thanks a lot, Francis.
I'm sorry, it just means I can't answer your question, but I will find. I think it's a good point, and I will find out about it.
Great, thanks a lot.
So thanks a lot. I think that there are no more questions here from the University of Szczecin.
Okay, thanks, Franco.
Thank you.
I have one question. Actually, it's a geology question.
Oh,
you talked about hydrothermalism, and you know that on Earth today, the main hydrothermal expression maybe are travertine deposits. Do you think that similar deposits could have been found on Mars? Could be found on Mars? If there have been enough carbonaceous material to deposit something like a travertine deposit?
I'm not too sure because when Mars was really active, it was more like the early Earth, and there the hydrothermal activity was silica-rich. I have not yet found travertines, early Archean travertines, and there's some association of barytes with hydrothermal activity on the early Earth, but not carbonates. So I think we can't exclude the possibility on Mars, but activity on Mars is more likely to be similar to what happened on the early Earth than the Earth today, because the Earth today is a geologically evolved Earth, whereas Mars has not evolved geologically. So I would say it's not impossible, but I think if there is hydrothermal activity, it's most likely to be most likely to be silicious. And in actual fact, the silica deposits that have been found, for instance, around Home Plate and elsewhere, are interpreted to, well, either to be silicious outflows or to be the effects of the hot gases leaching sediments and leaching out all other minerals except for silica.
Okay.
Sorry, all other elements except for silica.
Okay. Thank you for your presentation. It was very interesting. Thank you.
Thank you, Alessandra.